Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Thoriq Alfarizi and my student number is 220605525. And in this video, I'm going to talk about our last assignment, which is the student version of military application of of Spring Math System. So, um, we already have the file and the base which has 5 questions, and I already answered it in my last final test. But in this video, I'm going to talk about the coding to solve those questions. So we have number one, and the question for number one is the model the suspension system of a STT trailer while it is loaded with a satellite using these three different stocks, and those three different stocks is air coasters, cloud riders, and extreme shocks, which has spring constant and damping coefficients on its own. So the air coasters has 220 spring constants, and the damping coefficients is 100. The Cloud Riders has 59 for its spring constant, and the damping coefficient is 1050. And Extreme Shocks has 170 for its spring constant and 1110 for its damping coefficient. So, the trailer of a STT at rest will be loaded with a satellite with a mass of 1,800 kilograms. Assuming that the loaded trailer is at equilibrium, the displacement of the shocks before the trailer is loaded is 3 centimeters. So, and this is the code that solves it, which solves the plotting, and this is the plot for the solutions. So let's run it, and we have this plot, and we have the displacement in meters and the time in seconds, and it has the given damping and the critically damped. So each shocks has its characteristics. For example, in extreme shocks, there are no given damping, and it is critically damped. So the initial guess or the initial thinking is extreme shocks is much more efficient on holding the mass. Okay, let's continue to number two. And question number two is an ATEC engineers have specified that if the suspension system burns out on too many times, the component of the satellite could be damaged, which could cost hundreds of thousands of dollars to repair. Therefore, it is important to determine the proper shocks for the suspension systems of STTs to avoid any damage to the satellite. Topographers and engineers have determined that the force on the shocks in the most severe terrain at the highest speed that an HMMWV trailering an STT will attain can be modeled by the function Ft equals 200 sinus 4t times n, where t is in seconds, and assume that x0 equals 0 and x0 equals 0. Okay. And for question number two, we also have the code, which is this, and the equations is already installed here, and the external force is already installed too, so 200 times sin 4 times t. Okay, so let's run the code, and we have this plot. So we also have displacement and time, like the previous plot, and we can see the characteristics for air coasters. For example, air coasters has its starting point at 0 and reaches the high point of 0.05, and also reaching the lowest point in the middle of the time, and again reaching the high point too. And for cloud riders and extreme shocks, it basically has the same characteristics but different details. Okay, so that's it for number two, and let's continue to number three. The question for number three is the preferred option of the budget committee for the suspension system of the STTs are the shocks. Premium shocks is as per pieces, is K equals 25 Newton per meter, and the beta is equals 0 Newton times S per M. And the present reasonable data persuading our budget team that undamped shocks, although cheap, will not be sufficient. Consider the same external force function from part 2. Part 2 equals the second question. Okay. But with a variable frequency, i.e. ft equals 200 sin, is 4 times omega times t, where omega is the degree of roughness of the driving conditions. So for the question number three, we have a table, which is table one. Table one indicates that the displacement measurements of the trailer in meters, and we also have the code right here, and it is already installed too. So we have the time and we have the displacement. And let's run the code. And we have this plot, which has the displacement keep rising according to the time. And we also have this table, which has air coasters, cloud riders, and extreme shocks, and it has its max displacements and its minimum displacements. And as you can see right here. So, and that's it for number four. Eh, I mean for number three. Okay, sorry. And for um for number four, we do not have the code, but it is assigned by the previous code, which already has the plot, the data of the phenomenon, and describe the behavior of the trailer. So I already described the phenomenon in my paper, and this video is for the code only. So let's skip to number five. The question for number five is: before physical tests are completed by the ATEC, I have been tasked to, maybe you have been asked to run additional simulations of the STT trailer based system. In particular, ATEC senior engineers would like you to consider a scenario for which the trailer traverses a rugged terrain with exposed rocks, an environment the STTs will likely encounter. And a technique for modeling the rugged terrain is to express the force applied to the suspension system by each rock as an impulse. This can be done with a direct delta function of the form, where omega is the concentrated load applied at time. And to model terrain with n Newton equally spaced rocks, we can express the external force, or F, via several impulse functions, i.e. ft equals omega 0, sigma n, and n equals 1, and so on. Where where 2 is the time between impulses and the initial impulse occurs at c, and your job is to complete an analysis of the STC suspension system for a trailer traversing over rugged terrain. So, in question 5, we have a I are we are tasked to use Mathematica, and let me explain what Mathematica is. So, Mathematica is a code, programming language designed for Wolfram, and Wolfram is um. Let's search Wolfram Mathematica. Mathematica is a software system with built-in libraries for several technical computing that allows machine learning, statistics, symbolic computation, data manipulation, and so on and so on. So it is a proprietary software. So it is paid. And of course, I can't use a paid software for this video. And instead, I changed the code, the Mathematica code, to Python so we can run it freely. So I have already installed the question to this code. So this is basically the same like the in the Mathematica code, but instead I use Python. So let's run it. We have the plot here. It has displacement and time for suspension system displacement over time. So it is 0 all the way to the 50th seconds. So we close this and we have new plot, and it is suspension system displacement over time, or pi p equals 2 seconds. So we have 0 to 50 seconds, we have 0 displacements, but in 50 seconds, for some reason, we have 1.2 or more displacements or meters. And we close this one too. And I think that's it for the plot and the coding for 5 questions. So that's complete. And I hope you enjoy and understand. If you don't understand, you can comment down below, and I will try to fix or tell you the solution as soon as possible and as fine as possible. So, thank you for watching. I'll see you next time. Bye bye.